Good day, everyone. My name is Sebastian, and along with my teammates Kaliana and Paran, we will be presenting our research project on the design and simulation of triboelectric nanogenerators for energy harvesting. Here is the outline of the topics that we will be covering throughout this presentation. Miniature electronics are nowadays in great demand due to their high versatility and society's ever-increasing demand for portable electronic devices. Miniature electronics require of little power, therefore satisfying their load can be simply achieved by harvesting the mechanical energy that is highly available from their surroundings, instead of being directly supplied by battery banks. The development of such small-scale power is on high demand and is now a growing field known as nanoenergy. Triboelectric nanogenerators have become very popular in this field as they are a clean energy source that provides high energy conversion efficiencies and high power densities at low cost and low weight. All triboelectric nanogenerators are driven by two physical effects. The first one is contact electrification, also referred to as triboelectrification, and is the effect that generates static polarized charges on the contact surfaces of the materials. Then, the electrostatic induction comes into play, driving the energy conversion from mechanical to electrical energy. In particular, triboelectric nanogenerators excel at harvesting energy at low frequencies that can be obtained from human motion or from uncharted areas of wind, waves, and tides. To date, triboelectric nanogenerators have achieved power densities of 500 watts per meter squared and conversion efficiencies of 70 to 85%. Some of the current applications include wearable power sources, wave energy harvesting, as well as pressure-enhanced keyboards. On the right-hand side, you can see a triboelectric nanogenerator design for wave energy harvesting. For all triboelectric nanogenerators, there is a pair of surface charges that establishes a potential difference across a particular load. That means they have an inherent capacitive behavior, and therefore their output voltage can be written as the sum of two terms. The first term is the contribution due to the capacitive nature of the nanogenerator, and the second term is the open circuit voltage contribution that comes from the polarized triboelectric charges. On the right-hand side, we can see the equivalent circuit diagram for any triboelectric nanogenerator. The following sections on the operation mode and the material properties for triboelectric nanogenerators will be presented by my teammate Paran.
In this slide, we are going to illustrate about the four basic modes which can be used in triboelectric nanogenerators. So, depending on their characteristics, they can be used for different purposes. First one is about the contact separation mode. In contact separation mode, two dielectric layers are used with electrodes deposited at back of each layer, which is separated by a distance d. So using external force, two layers are brought in contact with each other and then separated. So when separating, current flows in the external circuit due to the opposite charge being electrostatically induced. So the alternate current is produced when opposite charges neutralize each other when coming into contact. The next one is called the lateral sliding mode, where a current flows in the external circuit when two frictional layers slide apart and their triboelectric charges start electrostatically inducing opposite charges on the electrode. An external circuit generates an alternating current by sliding in and out of the frictional layers. The next one is the single electron mode. In this mode, a single dielectric with an external layer is used either in contact separation or sliding mode. The ground connected electrode is connected with the friction layer, and the object which comes into contact with the friction layer generates an ordinary current. So this purpose this mode can be used for generating small amount of energies such as running, walking, and riding. The final one is called the freestanding mode. This mode has two electrodes which are located right underneath a moving freestanding dielectric layer. The motion generates charge distribution which drives the electron flow across the loop. In thing, the characteristics of materials plays an important role in the performance. So the selected materials should have the maximum ability to transfer charges. Charge transfer is determined by mechanical and chemical properties of the respective materials and their surfaces, including roughness, stiffness, charge affinity, electronegativity. The table represents the material list where researchers prepared as a guide for selection of materials. In the following two slides, we are going to state about the most important properties while considering the selection of materials. One is relative permittivity and another one is the surface charge density. The relative permittivity is defined as the ratio of substance permittivity to the permittivity of space or vacuum, provides the information with which a material can become polarized by placing an electric field, which means it indicates the energy that can be stored per unit of volume when placing an electric field. So the formula is to generate for the relative permittivity is epsilon r is equal to epsilon by epsilon naught, as epsilon r is mentioned as dielectric constant, and epsilon is substance permittivity by vacuum or free space permittivity. And the table represents the relative permittivity of range of certain materials which are based on the experiments and article status. We have used paper and silk on the positive side and polyethylene and Teflon on the negative side for our prototype. The next important factor to consider on the selection of materials for things is the surface charge density. The density may be measured or may be calculated. The ranking of triboelectric materials depends on their physical properties such as the tendency to lose and gain electrons. When two different materials comes into contact, it causes static electricity due to the excess amount of negative and positive charges. So, but the surface charge is defined as the charge allocated at surface per unit area is known as surface charge, where sigma is equal to Q by area, where sigma is the surface charge density and Q is the charge and A is the surface area. The table gives information on the surface charge density of some materials which were generated in an article and the experiment done. Hereby, my teammates will follow with the discussion on the simulation results and prototype.
With the COMSOL software, the open circuit voltage of several designs was simulated. First, the software was validated by mimicking in its entirety a triboelectric nanogenerator found in the literature and comparing the simulation results to those reported in the literature. The simulated device was a contact separation triboelectric nanogenerator with a single dielectric, as shown in Figure 5. The simulated open circuit voltage matched the literature results. Therefore, the following simulations investigated how the output of the device would change when having larger surface areas. As it can be observed in Figure 6, the increment of the surface area of a triboelectric nanogenerator provides higher output voltages. The following set of simulations model the output voltage for a contact separation triboelectric nanogenerator with two dielectrics, as seen in Figure 7. The chosen dielectrics were nylon and Teflon, as they are materials that have high charge affinities. The high charge affinity of these materials provides the triboelectric nanogenerator with a higher charge density after the surface undergo contact electrification. Lastly, the effect of the surface area was also investigated, and as it can be observed in Figure 8, increasing the surface area also increased the output voltage in a similar manner to the single dielectric simulation. This is in agreement with the theory, as having a larger surface area means that there is more charge accumulated at the surface. And now my teammate Kaliana will proceed to explain manufacturing methods for triboelectric generations, as well as the development of our prototype and its testing.
I'm going to explain on manufacturing technologies of triboelectric nanogenerators. We did a study and investigation into the existing technologies. The all-printed nanogenerator was made by 3D printing, 3D printing the structure, but the structure is used to transform the mechanical vibration into the sliding and sliding modes. But the nanogenerator layers are printed by piezoelectric inkjet printers. Actually, those are nanocellulose papers. Uh, so then the spherical the structure is spring-assisted multi-layer structure. Um, so then the electric thermogenerator based on enclosed tubular structure. Actually, there are two types: the semi tubular structure and full tubular structure. So those are like the one the electric materials is in the tubal form, while the other the material and electrode in a spherical form inside the tubular. So, for example, when it's floating on the water, the two layers are get contacted and generate the electricity. So, and here you can see the super stretchable nano generator is a special one. It is under research. It can be used as an electronic scheme. So, and one of the special one is a freestanding flat type generator. So, there are fabric type dielectric layers are woven into a flat. So, when it is mounted on the wheel, the vibrations are directly deployed for the energy harvesting. And the microcable structures textile. So actually, there's a it's the two layers are woven into a textile. So that's a special type. So and there's another the normal manufacturing method, the self-powered triboelectric micro liquid. So that is two type of liquid which are using the different fluid dynamic properties to make the sliding mode in between two fluid layers. So it would be the ideal for wave power generation. So and the spherical structure, the last one, the last electrical generators based on the fully enclosed the spherical structure, so that can be float on the water to absorb the vibration of water waves. So those are the summary of the existing technologies we studied into. So actually, we developed a few 3D printed layers. We used PLA and ABS. We used the facilities in the MAN prototype 3D lab. And we went to some discussion with the MANMED 3D printing lab. So actually, the main disadvantage of 3D printing is it is less abrasive resistant with its additive manufacturing properties. And other thing, the most of the readily available 3D printing materials such as PLA, ABS, and PETG are in the close proximity of the triboelectric series. So, and the higher end materials such as Teflon and nylon are less manufacturable, so they are available, but they are so rigid. So, another thing is we need to have the thickness, higher thickness, like 0.8 millimeters with 3D printing layers. And we moved into develop a prototype using thin films. We made two prototypes. One is with polythene and paper. Polythene as the negative and paper as a positive materials. So, and then we used the silk and Teflon. Actually, silk and Teflon are in the further ends of the positive and negative spectrum as shown in the figure. Um, so we expected that those gives out higher results. So those are the photos of our prototypes and the 3D design of the our prototype developed. So we use aluminium foil and aluminium conductive tapes as the conductive layers. Actually, we wanted to try out the glue effect also. So actually, those are the four modes we with two modes with two prototypes we developed. First one is polythene and paper in contact separation mode. So and second one is the polythene and paper in sliding mode. So it gives the better result than the first one. And the third one we did the silk and Teflon in contact separation mode. It delivered the better result than the polythene and paper, obviously. And finally, in sliding mode, silk and Teflon gave us the voltage above the 500 milliwatt. So those are the videos of the experiment we conducted with our prototypes. So and then we moved into our results. as you can see in the graph, uh, the Teflon and silk gave the better result, and of course we observed one thing. We observed is sliding mode uh, uh, gave us a higher voltage than the contact separation mode. So actually we assume that when we are doing sliding, we exerted more pressure than in the contact separation mode. So actually that phenomena can be explained by the cloud well model proposed by Professor Wang. As you can see in the picture, so when two materials are in contact, so the electronic cloud well are merged together. So when the force is the pressure increase, the height of the cloud well getting decrease. You can see. So when the materials are those cloud wells are merged, so the electron can be transferred from each material to other material easily. So that is happening as we the concluded when we exert the higher pressure in the sliding mode. So actually we managed to illuminate a LED bulb as shown in here with just the prototype we developed. It was 20 millimeter into 50 millimeter size. The illumination of the bulb was visible in the dark. So what are our future steps? So we would like to expand our research into a study how to deploy the triboelectric nanogenerator for tidal power generation, and we are going to simulate uh, the variation of the rate of mechanical vibration to study the effect on the power generation. So, and the meantime, we are trying to develop and focus on enhancing the manufacturability, reliability, and robustness, focusing more on materials and structures. And in the meantime, we would be looking for how to use the triboelectric nanogenerators in combination with electromagnetic generators to better the power generation using the tidal waves.
Miniature electronics have a very high demand for nanogenerators as mechanical energy is abundant and batteries are both expensive and hard to manage. Triboelectric nanogenerators present themselves as a promising candidate for both renewable and nanoscale energy generation. The manufacturing materials and the operation modes will determine the performance of any triboelectric nanogenerator. Therefore, they should be heavily considered in the design process. Simulations allow for the testing of multiple triboelectric nanogenerator designs and are preferred over experimental tests, which are often expensive and time-consuming. Doing simulations is particularly helpful as it facilitates the development of a prototype by making the process more effective and efficient. The simulation results demonstrate the importance of the surface area and the material selection, as they both heavily increase the output voltage when chosen adequately on a triboelectric nanogenerator. Here are the references cited on the presentation. We kindly thank you for your time.